Thank you very much. So first of all, I would like to thank Dongwook, Henri, and Tatiana for the kind invitation. It's really a great workshop. And yes, my topic, I guess, is in the spirit of cross-pollination. So it's not at the center of the interest of the workshop, but I think it has some interesting connections. So first of all, let me acknowledge my collaborators, Oscar Pozzo, who is a postdoc, and Stefan Tsirkin, a colleague who is now joining, actually moving back the same institute as me in San Sebastian. So here is an outline. So I'll start with the motivation. So I'm talking about optical responses in non-centrosymmetric crystals, and optical rotation is one of them, and directional dichroism is the other. I'll start with some phenomenology. And these things have been studied a lot in molecules, so I will review the microscopic theory that the quantum chemists have developed. There are some interesting origin dependence issues that I will touch upon. And then I'll move to the main interest that I have, which is formulating a microscopic theory for crystals. And it will have two desirable properties, which is gauge invariance and origin independence. Then I will try to connect back to the molecular theory. And finally, if time permits, I'll mention briefly something about optical sum rules and give a tight binding example of the formulation. So first motivation is natural optical rotation and circular dichroism by chiral crystals. Here is tellurium, elemental tellurium, where the atoms are organized along chains. They can be right or left-handed. And if you shine linearly polarized light along the axis of the chains, as light travels through the medium, the plane of polarization rotates at a constant rate per unit length. So that's the optical rotation. That's when light is in the transparency frequency range of the material. If it is getting absorbed, then left and right circularly polarized components of light are absorbed at different rates, and that's the circular dichroism. Second motivation is directional dichroism, and this happens in materials that break both inversion and time reversal. So tellurium only breaks inversion, and the best known example is Cr2O3, where because of the antiferromagnetic ordering of the chromium atoms, this would be a center inversion if there was no magnetism, but the magnetic ordering breaks inversion in addition to, of course, time reversal. One of the optical effects that happens in such systems is that light propagating this way and that way will have different phase velocities, and at absorbing frequencies, the absorption coefficient will also be direction dependent, sometimes called one-way transparency. So what these two phenomena have in common, I hope I will explain now. So I want to describe the current response to light, and I will do that by introducing an effective conductivity where the response to the optical field is described as a J in response to the optical E, but remember the magnetic field of light is not independent of the electric field. So actually, this coefficient contains the entire optical response, both to E and to B. And what we want to do, so this conductivity is a function of not only of frequency, but of the wave vector Q of light. And we want to expand it in powers of that wave vector Q. And I will go to first order. So at zeroth order, it is a tensor with two indices. A is the direction of the induced current. B is the direction of the field. At first order, there is a third index, which is the Cartesian component of the wave vector of light. Next, let's split this tensor into symmetric and antisymmetric parts in the first two indices, A and B. Natural optical rotation is described by the antisymmetric part of the first order tensor, and directional dichroism by the symmetric part. And these are called, all the optical effects that are described by the wave vector dependent conductivity are called spatial dispersion effects. There is a chapter in Landau and Lifshitz about it, of course. So now to the microscopic theory. So our task is to calculate from quantum mechanics this spatially dispersive conductivity. And I will split the problem into two parts. One is how to do it for finite systems like molecules, chiral molecules, or finite crystallites. And the other is for bulk crystals. And the theory for finite systems is very well developed. And I put here a good reference, which is a book that kind of summarizes a lot that has been done by the quantum chemists over the years. And let me give you a flavor of how that theory goes. So we shine light on our molecule. So it has an optical, electric, and magnetic field. And these oscillating optical fields are going to induce oscillating moments on the charge distribution of the molecule. And I will focus on three moments. Electric dipole moment, which I will call E1, magnetic dipole M1, and electric quadrupole E2. So here are the formulas. So here is the dipole operator, the circulation operator, and the quadrupole operator. And so the light is inducing these oscillating moments, and from them we can calculate a current like so. So there is the time derivative of the electric dipole moment, which is the more familiar term. Then there is the curl of the induced magnetic moment. And then there is a spatial derivative and a time derivative of the quadrupole moment, which may be less familiar to you, but it's also there. And then there are higher order terms that we will not need to consider. So now let's Fourier transform in time and in space. So time derivatives become minus I omega, spatial derivatives IQs. So we get a formula like this. And what you do next is time-dependent perturbation theory to describe the induced oscillating moments in response to the electric and magnetic fields. And there are susceptibility tensors that describe that. I will not write them down, but all I want you to pay attention to are these subscripts. So there are two optical matrix elements in each tensor. So for example, the dielectric susceptibility has an interference between two electric dipole matrix elements. The electric moment induced by a magnetic field, that's kind of a magnetoelectric coefficient, has an interference between electric dipole, magnetic dipole, and then there is also an electric dipole, electric quadrupole term that describes the induced electric dipole by a gradient of the electric field or an induced quadrupole by the electric field. So anyway, what we want to do is to plug these formulas back into the expression for the current and collect terms at the same order in Q. And for that, you have to remember that when there is a magnetic field, that also already carries a Q, right? So if you do that, what you find is that at 0th order in Q, you have only the E1 term. That is the familiar optical susceptibility. And at 1st order, you have E1, E2, and E1, M1, okay? So we have our molecule with occupied and empty states, so everything here is independent particle approximation, and we want transition matrix elements between occupied states N and empty states L. And so E1 is this simple expression here, the dipole transition. There is the magnetic dipole transition with the circulation operator and the quadrupole term. And the kind of funny thing about this is that, of course, any physical observable has to be independent of the choice of origin, but that's not the case for the individual matrix elements that I'm showing here. Well, actually, for interband transitions, the electric dipole matrix element is origin independent because of the orthogonality of the orbitals, but the other two are not. So I'm showing here the transformation laws, and they do depend on the origin for L and N different states. But when you collect everything in the physical response, of course, that result, the origin dependence of one term will cancel that of the other. So what we have then is a formulation that in the electric dipole approximation, we have a conductivity where everything is manifestly origin independent. The spatial dispersive conductivity is an origin-dependent combination of origin-dependent terms. So that's how it is. So we have our microscopic theory for finite systems, which is the multiple theory. And now we would like to do the corresponding theory for bulk crystals. So how are you going to proceed? First, let me remind you from David Van der Wield's talk yesterday. The problem is that the multiple theory cannot be readily applied to periodic crystals because the moments are ill-defined in terms of the periodic charge density. And the famous example is the ground state polarization. And we know that the proper way to do it is to recast the electronic polarization as a Berry phase of the Bloch states, which is an integral of the Brillouin zone of the Berry connection A, written here. Okay, so since the multiple approach does not really work, we have to do something different. What we're going to do is to evaluate the conductivity starting from Kubo linear response. And then we want the first order in Q conductivity, so we're going to take a derivative with respect to Q of this Q-dependent conductivity at Q equals 0. And we want to express the result in terms of matrix elements that have three desirable properties. They are multipole-like, they are origin-independent, and they are gauge covariant under, this is what I mean by gauge transformations, by the way, is changing the Bloch states by K-dependent phase vectors. Okay? So before proceeding, let me just remind you some basic facts about conductivities. A conductivity can be divided into Hermitian and anti-Hermitian parts. The Hermitian part is absorptive, the anti-Hermitian is reactive, but it can also be divided in the two first indices A and B into symmetric and antisymmetric parts, and that's how the two decompositions are related. And the Hermitian and anti-Hermitian parts are related by a Kramers-Kronig relation. Okay, don't be intimidated. So this is a standard Kubo formula, but yeah, it looks messy. So I've written two of them, one for the Hermitian part, one for the anti-Hermitian. Let's look, okay, the Hermitian has a delta function because it's energy conservation, you're absorbing energy. Let's look, for example, at this one. So basically what do we have here? We have some energy denominators. So by the way, it's a sum over N and L states. The N states are at K minus Q over 2. So K is the crystal momentum, Q is the wave vector of light. The L states are at K plus Q over 2. Omega Ln is their energy difference in the denominator. There is a difference in occupation factors in the numerator. And then there is an optical matrix element in this last line here. Okay? And we want to differentiate this entire expression with respect to Q at Q equals 0. So there are three objects that depend on Q, the omegas, the Fs, and the M. Differentiating the first two is totally trivial. By the way, differentiating the second is only necessary for metals because for insulators, the occupations are constant in the Brillouin zone. The tricky part is the differentiation of the optical matrix elements. And let me write again here the optical matrix element. It depends on Q in 4 places, here, there, there, and there. So when we take the Q derivative, we get a total of 4 terms. Just some notation. Now to simplify things, I write K derivatives just like this. Partial C is a partial K derivative along Cartesian direction C. And I've introduced the velocity matrix elements. The velocity operator is 1 over h bar times the gradient of the K-dependent Hamiltonian. Okay, so first problem. We have K derivatives of the Bloch states. And the problem is, when you transform a Bloch state like so, when you do a gauge transformation, the gradient of that Bloch state does not transform in the same way. So we say that it does not transform in a gauge covariant manner. So the first trick I will introduce to tame this complicated object is to replace everywhere that we see a K derivative of a Bloch state, I'm going to replace it by what's called a covariant K derivative, which is simply, and I will denote that by a capital D. It is simply taking the ordinary K derivative of the Bloch states and pre-multiplying it by the projector onto the complement space of that state. And you can write it in this way. So the covariant derivative is the ordinary derivative plus a correction term that involves the Berry connection. And the neat thing is the following. If you make this replacement in this expression, of course, term by term, things will change. But the changes will cancel pairwise between the two terms in each line. Okay? So that means that so we can now write things in terms of a more well-behaved form, so gauge covariant. That's great. And by the way, in materials like Cr2O3 that have PT symmetry and the bands are Kramers degenerate, you can introduce a non-abelian covariant derivative where you basically project the k-derivative out of the degenerate manifold of the twice degenerate band. So no problem there. So second point I want to make. This formula has velocities. So there are here explicit velocity matrix elements, and then there is the velocity operator here. So we could say that we are in the velocity gauge. And I would like to make contact with the multiple theory, so I would like to go to the length gauge, or more precisely into the multiple gauge, because length gauge is an expression that applies in the dipole approximation. And for that, I will introduce another mathematical manipulation, which you can prove in one line, but basically this is it. So I will replace the velocity operator acting on a block state by this expression here. This may not look familiar to you, but actually if you multiply on the left by a state UL, then it becomes a velocity matrix element. It just gives you the familiar decomposition of the velocity into intraband, band gradients, and interband matrix elements. And I've introduced here a calligraphic A that is a Berry connection defined in terms of the covariant derivative. So it's basically the off-diagonal components of the Berry connection matrix. The diagonal components are not gauge covariant, but the off-diagonal components are. Okay, so we do these two tricks, and you work out what you get, and you collect terms. And the spatially dispersive conductivity will look as follows. So remember that for finite systems, there were two terms, electric dipole, electric quadrupole, and electric dipole, magnetic dipole. For bulk crystals, it turns out that there are three terms. The first two are bulk analogs of the molecular ones, and I will call them intracell. And then there is a third matrix element that has no correspondence in the molecular theory, that is actually electric dipole times a band velocity, okay? So in the limit of a molecular crystal, where the crystal is composed of non-overlapping molecules, the bands are flat, the band velocity vanishes, and this term goes away, and so that kind of makes sense. Okay, so I'm writing here what you already saw, the form of the multiple matrix elements for molecules, electric dipole, magnetic dipole, electric quadrupole. I don't have space here to write the full formula for the bulk analogs, but the electric dipole is going to be basically the off-diagonal Berry connection, and I will call magnetic dipole with a bar on top. You will see the formula in the next slide, and same thing for electric quadrupole like with a bar, and I will write it in terms of a tensor which I will call G. Okay, what is the form of those tensors? So the calligraphic A is the gauge covariant Berry connection. That's the electric dipole. The M bar looks like this. So it has covariant derivatives of the bra and the cat with an age minus an average energy of the two states sandwiched in the middle. And the G has this form here. So this tensor, well, it's a symmetric tensor. And it has a kind of an inner product of the covariant derivatives of the two states N and L. First observation, because there are only covariant derivatives here, these objects are manifestly gauge covariant, okay? You can also show, not evident, but they are also origin independent. You will see it explicitly in a limit later on. Second thing, what happens if you expand the covariant derivative and you write it explicitly in terms of the ordinary derivative plus extra stuff? How do these formulas look like? So I'm basically expanding. So the first one is very simple, is the off-diagonal Berry connection. The second one is this one here. So there is now some diagonal Berry connections and some off-diagonal ones and an energy difference here. Anyway, so that's what it looks like. Now what I want to do next is to take the special case where L and N are the same state. And note that in that case, this second term vanishes because you have En minus El. And then here you have the average energy, so you just get En. And what you recover in that case is a formula that David Vanderbilt showed yesterday, is the intrinsic orbital moment of a block state. That's the M bar. And the G is a quantity that was also introduced by David in the field of electronic structure and is known as the quantum metric. And so, so the off-diagonal matrix elements are gauge covariant, and the diagonal ones are gauge invariant. Okay. Another observation, when we write now our spatially dispersive conductivity in terms of these matrix elements, there are intraband and interband terms. And these intrinsic orbital moments give an intraband contribution to the antisymmetric part of the spatially dispersive conductivity, the part that describes optical rotation. So it is like an intraband contribution to optical rotation in metals. And this has been discussed before by several people. As for the quantum metric, it gives an intraband contribution to directional dichroism in metals. And this was discussed in a paper by Gao and Xiao. They called it the quantum metric dipole. We could also call this the orbital moment dipole. But interestingly, in this paper, they were only able to establish this result in the limit of two-band models, which is, in a sense, a very special limit. And with our formulation, actually, we managed to show that the interband quantum metric appears rigorously for infinite number of bands as an interband contribution in metals, without restriction to two-band models. Yes, thank you. Okay, now, what I would like to do next is to relate back to the molecular theory. So I want to consider the limit where our bulk crystal is composed of non-overlapping molecular units. And you can work out, let's call phi's, the wave functions, the orbitals of the molecules. You can work out what the matrix elements that I wrote before for Bloch states reduce to in this molecular limit. And the dipole matrix element is just what you would expect, but off diagonal. And these are the more interesting ones. So, and this is really the reason why I've introduced the bar notation here. So, for example, the M, the magnetic dipole matrix element, is like a circulation matrix element between the two orbitals, but in a reference frame whose origin is at the center, the average location of the two orbitals involved in the optical transition. And the same thing for the quadrupole matrix elements. So they are quadrupole-like, but they are defined relative to this special choice of origin. So clearly these are origin independent, right? Because this is an intrinsic origin choice. So that's what I meant, that in some limit it's clear that these matrix elements are origin independent. So to summarize, for finite systems, we have the standard formulation where spatial dispersion is written as a sum of origin-dependent terms, and now we have a new formulation in terms of origin-independent terms. There are two of them. For bulk crystals, we have a formulation in terms of three types of matrix elements that are origin-independent and gauge-invariant. Okay, some words about sum rules. I want to mention one that everybody knows, which is the F-sum rule. So if you take the symmetric part of the absorptive conductivity in the electric dipole approximation and you integrate the absorption over all frequencies, both intra and interband, you get basically the number of electrons. There is a sum rule for natural optical rotation that is very well known in the chemistry literature since the 1930s, which is a similar integral for the natural circle dichroism gives 0. What we've discovered, actually last week, is that if you do the same thing with our formulas for crystals, you get 0 in a very interesting way. So the sum rule is satisfied, but for topological reasons. This omega is the Berry curvature. This is a very famous formula in some quarters. So let's say 10 people. It is the absence of a chiral magnetic effect in equilibrium. You can find it actually in David's book as well. So, but anyway, this does vanish, so the sum rule is satisfied for Bloch electrons. Okay, I have 1 minute. Let me give a tight binding example. This is a chiral tight binding model. And I will go very fast, but what I want to show is some calculations that compare the finite crystallites with bulk calculations. And the main point I want to make is that the two calculations agree very well. Let's take one tensor component. For finite crystallites, there were 2 terms, remember? And for bulk crystals, there were 3. So if I do a comparison term by term, there is no agreement. For example, the E1, M1 term. Likewise, for the E1, E2 bar term, there is no agreement, but the total agrees perfectly. And the reason is the existence of this intercell term, which is a little bit like the itinerant circulation in the orbital magnetization story. And that is the one that restores the perfect agreement. Okay, so some acknowledgements. Thank you for your invitation and your attention. And here is a summary. Thank you.